Let's look at what we're going to look at today. Okay. So everyone can see the screen, right? Okay. Right. So for today, we'll go into the chapter 3. Okay. In fact, there's a chapter 3, 4, and 5, which we'll cover in this 2 weeks time, this week and the week after your semester break. Essentially, they're all dealing with energy. Sorry. They're all dealing with energy. Energy and energy transfer. That's what this remaining, I'll call like a second half of your thermodynamics, because the second half of the subject is on solid mechanics. So this first half of the thermodynamics, the first half we look at the fundamental, the laws of thermodynamics. We look at a lot of definition, especially what is substance, and then we look at how do we find the state of thermodynamic for substance, right? And specifically, we look at two types of substance. One is a pure substance, and second is ideal gas, something that's light enough. We learned that we can approximate the state of thermodynamics of it using ideal gas equation. It's like a simplification to make the calculation easier. Okay, so understand that now we move into slightly more advanced stage in thermodynamics, I would say. And really, this is what thermodynamics is all about. We want to look at energy. We analyze energy. Okay. And if we analyze energy, then of course, there is a transfer of energy in a system in general. Okay. So that's what we're going to look at in this final three chapter. Okay. And the way it is being structured, chapter 3 is about introduce you to energy. What is energy? How do we define energy? How do we calculate energy? Okay, in a more general way. So that will be chapter 3, which is what we're going to look at today. I think today we'll do like as usual. We have 3-hour class, so we'll do like a half-half. The first half we'll probably look at the introduction of energy in general. And then we'll go into the chapter 4, which will analyze the energy and energy transfer in a closed system. Okay, and for those that who still remember, closed system basically means the mass transfer is 0. There's no mass transfer. In fact, I can't write it as 0. It's really none. So it's a closed system, no mass in, no mass out. But then there can be heat in, there can be heat out, there can be work in, it can be work out as well. Okay. And then the week after semester break, we're going to look at chapter 5, which will be looking at open system. The same energy and energy transfer, we'll look at 2 different systems. That's what the whole chapter 3, 4, and 5 is. So open system, of course, there's a mass exchange. So other than heat, other than work, there's a mass exchange as well in the system. Okay. So first, let's understand what is energy, and then energy transfer. How do we define energy transfer? Okay. So for this chapter, okay, it's really about the concept of energy. So therefore, you learn about the concept of energy and how to define the various forms of energy. Okay. And then we'll be looking at what is internal energy, the nature of the internal energy. And then the concept of heat. We talk about there's heat, there's work. So what are they? Okay. So the concept of heat, later on the concept of work as well, and then the various form of work, and then the various form of heat. Mainly heat transfer. Heat just heat. There's no various form of it. Okay. And then the similarity and differences in heat and work. They are all energy, really, but then it's a different form of energy, so we call them differently. So there's something different about them, but then they are generally similar. They are energy. Okay, and because it's thermodynamics, so now we go back to the first law of thermodynamics, which basically says that, if you still remember, energy cannot be destroyed or created. It's always conserved. So energy transforms from one form to the other, or it has to go somewhere. Okay, we'll be looking at energy balance, and then the mechanism of energy transfer to and from a system. Right? It cannot be destroyed, but then it can transfer from one place to the other, from the system to the other places, or from other places to the system. And the most important part, of course, based on first law of thermodynamics, is the energy has to be balanced. In the end of the day, it cannot just go missing. As simple as that. Okay, and we'll be looking at moving boundary work as well, such as a piston, which means the boundary, which usually we draw as the dotted red line here, that boundary will move. So the minute it moves, it is doing work. So the boundary itself is doing work. So that kind of work, we call it the boundary work, basically. Okay, so it's a very general about what energy is about, and then how energy is being transferred. So as usual, we will start with definition, okay? Because without definition, it's really quite difficult to explain what is energy and how energy transfer. Okay, so energy, as you probably learned up until this point, there are many forms of energy: thermal energy, mechanical, kinetic, potential, blah blah, electrical as well, magnetic energy, right? On the chemical side, we also have chemical energy and nuclear energy, of course. Okay, so the sum of all these form of energy, we call it the total energy, right, as E. Okay, and we can express this in the specific term as well, which we write in the small cap, which is per mass, if we want. Okay, and the unit for energy is really joule, SI unit, of course. The other empirical unit, you might have the BTU, you might have the calorie, even the food that we eat, there's energy in it, transfer to us. That's how we get the energy from food, right? So there are others unit of energy, for energy, sorry. Okay, but for research, for academic purpose, we always use the SI unit, at least our academic standard. So we use joule, basically. It can be kilojoule, megajoule, terajoule, that's prefix, indicate the magnitude. But the base SI unit is always joule. Okay. And in most application, the absolute magnitude of the energy is not so much of our concern in thermodynamics. What concerns us more is how much is the changes. Because effectively, we want to look at from state 1 to state 2. So it's the changes in between, how much the energy involved is what interests us more. Okay, so when it comes to energy, it's really we're talking about mostly the changes, and therefore why it's called energy and energy transfer, because the process of transferring is what caused the state change from one to another. Okay, and generally we can divide the form of energy into two categories. One is macroscopic, one is microscopic. Okay, macroscopic is something larger we can see, such as kinetic energy, potential energy. Okay, we can't see the energy, but then it's something that we see it moving, we see it changing, we can know there's an energy change in the process. Okay, the microscopic is something that we might need microscope to look at it. Okay, because it happened in the molecular structure of the system. So it's not something that we can see or visualize by using our naked eyes. So this usually involved in the molecular activity, like the change in the molecular energy when it when the substance vaporizes or when it melts. So there's energy change in the process, energy transfer in the process, but then it's in the molecular level. Okay. And the sum of these, the sum of all microscopic form of energy, because it's not so much of our concern, we call it the internal energy, basically. We write as U. So to put it simple, E, total energy, is basically internal energy, which is the sum of all microscopic form of energy plus the, I will just call it the all macroscopic energies. Okay, so this is all the microscopic, and then we plus all the macroscopic energy. So this can be the kinetic energy, can be the potential energy, can be any other form of macroscopic energy. Okay, so E usually we write as the total, everything, sum them together. That's the total energy. Okay, and let's go into the internal energy slightly. Okay, even though not so much of our concern, but then it's good to know, because moving forward, there might be some of the internal energy that might interest us. Okay, so internal energy is sum of all the microscopic form of energy. Okay, specifically, there are, sorry, just a minute. Sorry. Yes. So internal energy is the sum of all the microscopic energy. So specifically, we're talking about 4 types of microscopic energy. Okay. I'll start from the bottom. Nuclear energy. This is the energy that bond the nucleus of the atom together. So between nucleus, proton and electron. So the energy between them, we call them the nuclear energy, which is very, very, very microscopic, of course. Okay. And then there's a chemical energy as well. The energy associated with the atomic bond in the molecule, for instance, H2O, right? So 2 hydrogen, 1 oxygen, they are bonded together. So the bond itself, the energy, we call it the chemical energy. Okay, so slightly microscopic, sorry, slightly macroscopic, slightly larger than the nuclear energy for sure. Okay, and then we have the latent energy, which is you have molecule of this, you have molecule of this, then the energy between them, the latent energy. So when the substance evaporate, the distance become larger, the energy got released, or we need energy to break it, right? So that form of energy we call the latent energy. Usually during phase changing, it will be released or is required for phase changing. Okay. And then there is another form of energy called the sensible energy. So this is the internal energy of a system associated with the kinetic energy of the molecule. Obviously, in a gas, in slightly on the liquid, but then mostly in the gas, because it's a kinetic energy. So the molecule is just moving around, not so much the latent energy anymore. So these are the 4 main energy, okay, available in the internal energy. So the way that usually we classify them, we try to break it down as detailed as possible, but then still keep it as simple as possible. In engineering field, we always do that. Okay, so usually when we call thermal energy, it's really just the sum of sensible and latent energy. Okay, so for internal energy, really is the thermal energy, which is a sensible and latent energy, which means the total of this plus the chemical, the one inside, 2 hydrogen and then 1 oxygen. So the chemical and the nuclear energy together. So it's just a definition. So something that you probably should get to know and then remember it until your test, at least, I would say. Okay. So this is how we define internal energy, really. Okay. And then the macroscopic energy, something that we can visualize. Okay. So the most common one is electrical energy, kinetic energy and potential energy. Okay, so I trust that you all know what is kinetic energy, what is potential energy. You are from physics field. You must have learned this in your secondary school before this. Okay, kinetic energy is processed with the movement. There's motion, and then there is kinetic energy. The definition of it, the equation for it, be mv squared over 2. Okay, or we can write in the specific terms per unit mass. We therefore write it in the small cap, which is Ke, big Ke, divided by mass, become the V squared over 2. Okay? And then the potential energy is the energy possessed by the system as a result of elevation in a gravitational field. Of course, when the object is sitting on the ground, it itself possesses a potential energy as well, right? But what concerns us more is when we raise it to a higher place, then how much it gains in between. Okay, so the changes in the height. So how much it gained from here to here, which is why energy is about the changes. More important, more than actually how much is the absolute potential energy it has when it's sitting somewhere. Likewise, for kinetic energy, the object might be already moving at one velocity. At one velocity. It already possesses kinetic energy initially, yes. But then what concerns us the more sometimes is when it moves to a second speed. So how much is the kinetic energy gain or it lose in process? Okay. So really the total energy in the system, we write at this way. E equal to U, which is the internal energy in the microscopic level, plus the macroscopic level. Okay, so that would be the total energy in the system. We can write it in a per unit mass as well, divided everything by the mass, then we get the small cap. Okay, and expand with these two equations. So then we get this part here. And all of these are energy, Joe, which means time is not related at all. Okay, but when we involve time in the equation, there's a rate, there's a change, the rate of change in the energy. Okay, so then we put a dot at the top. Okay, so the specific energy, we can't put a dot at the top because that's the energy per kilogram of substance. There's no time involved with that. Where the time comes in is how fast the mass actually change, which means the mass flow rate, the m dot. So the E itself still, sorry, we should write kilo. If we look at the unit, E is still joule per second. The mass flow will be kilogram per, sorry, what am I writing? The E is still joule per kg. Okay, and the mass will be kg per second because how fast the mass change. So if we cancel this out, eventually we get the capital E with a dot at the top. This is the rate of the change in the total energy. We get joule per second. Okay, so joule per second which also equivalent to watt. Okay, when we heard about kilowatt, megawatt, or just watt itself, those are the rate of energy change, or sometimes we call it power, basically. Okay, so power is basically with time involved. Okay, and the way we calculate mass flow rate is really, it basically means how fast a volume of, if we look at here, it basically means how fast a volume of a mass is actually changing in the system. Okay, so obviously the way we calculate it is to calculate the volume first, and then we multiply with the velocity. Okay. So sorry, rho AV. Rho AV, yes. So A is the area. Okay, and rho is density. So we know that for this area of the mass, how much is density? So that will give us the total amount of mass that will actually pass through it. Process in this area here, and then how much the velocity that is actually moving. So from there, we basically can get the kilogram per second. So the equation, sometimes we just have to, some of the equation, when it's too fundamental to be derived, so we just have to remember how the equation is actually. Okay, so that's how we evaluate the mass flow rate, really. Okay. And then let's go into what is heat and what is work. Okay, heat we write as Q, work we write as W. Okay, this is not unit, so it's not watt, but the symbol we write as W. Okay, or in a specific term, we write in the small cap Q and small w. Okay, specific term, absolute term. Okay. So the difference between heat and work is that heat always involves the change in temperature. As simple as that. You add heat to something, temperature change. You remove heat from something, the temperature drops. Okay, so whenever there is an energy transfer, if it is associated with temperature change, then there's a heat energy involved. You can think it that way. Otherwise, it's purely because of the work. Okay, and for work to call it work, there must be a force acting through a distance, because the definition of work is really F multiplied with X. The force multiplied with distance, how much is being displaced. Okay, and in a system, if we draw some boundary as this, okay, closed system, of course, we draw it four sides, so there's no mass exchange. Okay, heat can go in and out from the system. So does the work. Can go out, can go in. Depending is going in or out, we will write it as positive and negative. So positive, negative really means go in or out. Okay. So for heat, usually if it's negative, it's a heat losing by the system. Perspective is at the system. The boundary, sorry. We look at the boundary from the perspective of the boundary. Okay. If it's positive, then the system is gaining energy. Okay, so this that's how we assign the positive and negative. Okay, for work is the other way around. Okay, so when work is being supplied to a system, which means going in, we call it negative. Okay, opposite to heat, basically. But when work is being produced by the system, which means going out, we call it positive. Okay, so from the perspective of the system, if there's a net work going out from the boundary, then it's positive. If it's taking work, then it's negative. Okay, so really the difference between heat transfer, heat always being transferred, okay, and work is also being transferred as well, even though we hardly call it the work transfer. Okay, so the difference between heat and work is really whether there is a temperature difference involved. If there is, then it's a heat. If no, then it's a work, as long as there's energy changes in the system. Okay, so that's how we draw the differences between them. Okay, right? So, yep, this is pretty much like how I draw earlier. Okay, so in the closed system, just remember mass is constant because there's no mass exchange. This is a closed system. Okay, we will start by analyzing the closed system in chapter 4. And later on in chapter 5, we'll be looking at open system. Because once you understand closed system, then to understand open system is easier to do because you already understand how the energy balance works. So now we just add on top the mass balance. And for instance here, this is a heat transfer basically. Okay, so whenever there's a heat in there's a change in temperature, and then this is definitely a heat, not a work, basically. Okay, that's how we differentiate it. Okay, and the heat transfer, the heat energy Q, okay, we can also express it in a per unit mass, so therefore in a specific term, small q. Okay, and if we integrate the rate over time, which means we multiply the rate over time, joule per second, multiply with, sorry, time will be second, we can get the total amount of the heat energy being transferred from one location to the other. Okay, and just a few more examples here. Okay, so for instance, there's a baked potato, which means temperature is quite high. Surrounding temperature is lower temperature. Okay, so then there's an energy transfer from the potato going out. Okay, so there's a temperature, as the heat being transferred out, the temperature of the potato dropping. So therefore, this is a heat transfer. Okay. On the other hand, if we have a system which is fully insulated, then there will be no heat transfer in the process, which means the temperature doesn't drop. Okay, for instance, like your thermos that you use to contain hot water, even though eventually there are still some heat losses, the insulation is not so good. There are still some very small amount of Q going out. So I shouldn't write Q dot. Okay, it should be just Q. Okay, but if you can completely isolate this, insulate the whole thermos, which means your temperature, if you pour in hot water, it will never become cold, then it's a fully insulated system. Okay, so in that case, Q will be 0. If there is energy changes in the system, then it must be because of the work. Okay. So far, any difficulty to understand what energy is? Any question by anyone? Yep. Okay. Yes, I think heat okay, right? Heat go in and heat go out. Mm, mm. Okay, because usually this system is a device when we draw a system, even though we draw like a box only, but most of the time it's a it's a machine or something. Okay, so when work goes in, it basically means it takes energy. This system itself take energy. So which is why we call it negative. It's consuming work. But if the machine is doing, for instance, you can imagine this as an electric motor. Okay, the system is an electric motor. So when it's consuming electrical energy, which is in terms of work, then we call it negative. So that for it to produce the work, positive work here. Okay, so the electric motor itself is a boundary. What it consumes in terms of work, we put it as negative. It's just a sign convention, really. When the motor is rotating, driving something, then it's doing positive work. Okay, so it's really the system is consuming or is doing. If you imagine this as you yourself, what you eat is we call it negative, basically. Sorry, no. What you eat is a heat, actually. I shouldn't use that example. Okay, but if you are using let's say robotic arm to do a work, right? The robotic arm is moving you, then that is a negative work doing to yourself because you are consuming the work from outside. Okay. But if you're just doing work by your own, then that is a positive work. You finish your homework, it's a positive work. It's a sign convention. I do notice that it can be a bit confusing because it's in relative to the system itself. I hope that helps. Okay. Okay, right then. So let's look at a few example quickly. Okay, all these example are, I think, explanatory. Okay, it's a subjective question, not a calculation. Okay, so it's a burning of a candle in the insulated room. So we have a room fully insulated on the side, which means there is no Q involved. Doesn't go out, doesn't go in either. Okay. So a candle is burning in a insulated room, sorry. Okay. Taking the room, the air plus the candle as a system, okay, which means our boundary is here, as you can see the red dotted line, which I just draw over here. Okay, so that's our boundary. Determine if there is any heat transfer during the process. Of course, no, because it's a fully insulated. So that's the answer for the first one. It's a fully insulated, so there's no heat transfer in the burning process. Okay, and if there are any changes in the internal energy of the system, what happens if you burn a candle in a closed container? What do you think will happen? You feel hot, right? Because temperature will increase. In fact, if you get closer enough to the candle, you feel the heat. Let alone now it's a fully insulated room. It's like in the insulated room, you burn a fire, then over time the temperature will increase. So in that case, there is a change in the internal energy in this system here, but then there is no energy exchange in the to the ambient. To the outside of the system. Okay. So what happened is the energy inside the candle got transferred to the room. Okay. But within the room to the outside, there is no energy transfer. Okay. And U is the internal energy of the whole system. Let me just write properly. Okay. So U is the internal energy inside this whole system. And it is not just the thermal energy. If we go back to the definition, U is all the macroscopic energy, which is here. Okay, sensible energy, latent, nuclear, and chemical. Okay, so what happened is inside the room, the air gain energy. Okay, maybe I can explain it this way. If we're taking the system boundary as a candle only, okay, candle itself is a system boundary, then yes, there is a change in internal energy in the candle because there is a heat transfer into the room. Okay. If we look at the air in the room itself, which means there's a cavity of the candle, the air is gaining. This is decreasing, this is increasing. Make sense? This is the air. This is the candle. Okay. But when we put them together, which is this whole room here, there is nothing going out or going in. Okay. So the U in the total system, the air plus the candle, never change. Okay. So the delta U here is basically 0 of this system. Okay. So in thermodynamics, it's very important where we draw the boundary. Okay. Because if the boundary here, as you can see, is a candle, then yes, the delta U is negative, it's dropping because as it burns, it's losing its material. So then the molecular energy is being released, the microscopic energy is being released, turn into the heat. Okay. Likewise for the air, it's receiving energy from outside. If we don't look at the candle, we just look at the air itself, then the delta U is positive. But if we combine them together between this room itself, the candle and the air, they are exchanging heat in between one another. Okay. But as a total, they don't get leaked out into the system, or there is no net energy going into the system. So therefore, the delta U here for the whole room is actually 0. Okay, so that's what the answer for this question here. Okay, so in the end of the day, the delta U of the system, which is the room plus the candle, is actually 0. Okay. Second example. Okay, so here is a heating of a potato in the oven. So we have a potato initially 25 degrees Celsius, okay, being baked in the oven, maintained at 200 degrees Celsius. So which means now the same again, we can look at it in 3. The question wants to know that is there any heat transfer during the baking process? Okay. If we look at the potato itself, the system boundary is a potato. Okay. There is definitely a Q in. So delta U will be positive. Okay. But if we are looking at the A inside the oven, this is a potato. This is the A. Okay. It's definitely transferring heat out into the potato. So delta U is negative. If you don't run the oven. If you run the oven, there'll be a work into the air because there's something heating up the air to maintain it at temperature 200 degrees Celsius. If you don't run the oven, you preheat it 200 degrees Celsius, you throw the potato in, over time, it will cool down because all the heat transfer into the potato. Okay. So the question is asking whether there is a heat transfer during the baking process. Okay. So for this question here, you can see the answer here is actually not a well-defined problem because first, the question didn't tell us whether there is a electrical energy running the oven or not. Second, where is the system boundary? So we can't actually answer this question. Okay. But if here, okay, same oven just now. Okay. Now the question wants us to take the system only as the air of the oven. Okay. So now the question draw a clear boundary between, which is the air only, which is this one. Okay. So then if there is no external work coming in, sorry. If we're just looking at this air here, okay, of course there's a heat transfer into the potato. Okay. And if there is a external energy coming in to maintain it at 200 degrees Celsius, then there's a net energy coming in. But what form of energy is this? Okay, so for this is either heat energy or it is a work. Okay, and this is the oven. So therefore, it is not taking the heat from outside to heat it up. It is using the electrical energy. So therefore, it's in the form of a work, really. Okay, because there's no delta T from, sorry, there's no delta T from, it's not the delta T that drive the energy going in. Okay, it might be confusing to look at this way, but now if I draw the same potato inside a pot, now I'm burning gas to boil. The same process, I'm still cooking the potato. Q go in. So now I'm looking at the water. Okay. So there's energy out from the water going into the potato, of course. But there's also energy. I maintain it at 200 degrees. So in fact, it is water, so it cannot be 200. So 100 degrees Celsius. Okay. And then to maintain 100 degrees Celsius, there is an energy coming into the water to maintain it. Otherwise, as we cook the potato, the water temperature will drops. Okay. So for this energy, if I'm burning gas to cook it, okay, is driven by temperature difference. The temperature of the flame probably 100 degrees Celsius. Here is 100. So this energy transfer is in fact heat. It's not work. Okay. So I think this is easily understand. So the same concept here. This is 200. There is no temperature difference that drive this. So therefore, this form of energy is a work, really. Okay. So the question asks whether there's a heat transfer during the baking of the process, if we are taking the system boundary as air inside the oven. There is a heat transfer to the potato, but from outside into the air, it is not in the form of heat transfer. It's in the form of work, electrical work specifically. Okay. If we are cooking using gas, then yes, this is a heat transfer. So it's just a different form of energy that we try to identify. So really to differentiate between heat and work is really, it is driven by temperature difference or not. Okay. And just now was mainly heat. Yes, just now was mainly heat, Q. Okay. So then let's look at work. Okay. So work, okay, electrical work, we can't see something moving because what moving is the in the molecular level. Okay. But most of the other works, we can see things moving, like for instance, rising piston, pistons moving, rotating shaft. Okay. So all those are work basically because it's not driven by temperature difference or it's not caused by temperature difference, to put it simple. Okay. And if the work is going into the system, like how we said earlier, then it's negative. If the work is going out from the system, which means the system is doing work, then we call it the positive work. Okay. So the same example just now. So you can see the same question as the same example as just now. Okay. So it says that a well insulated electrical oven. Okay. So it's being heated through heating element. If the entire oven, including the heating element, is taken as a system, which means the whole oven inside is taken as a system, determine whether there's a heat or work interaction. Okay. If it's a well insulated, so therefore Q is nothing. Okay. But as we run the oven, definitely we know the temperature will increase. So there is a Q in. Sorry, the U in the system is definitely increasing. Okay. So if it's not because of the heat transfer, then therefore it must be because of the work. So there is a work transfer in this well-insulated electrical oven when it is running, of course. Okay, when it's heating through the heating element. So that work is basically the electrical work. Okay, and because it's going into the system, so this work is negative. Okay. So again, the difference between heat and work, heat is due to the temperature difference, really. If there is a changes, okay, the delta U is not equal to 0. There is changes in the internal energy. Then there must be heat or work involved. Okay. And if it's not because of a temperature difference, then it must be work. If it's because of temperature difference, then it's a heat. Okay. Sorry, just a minute. Okay. Okay. How can we establish a adiabatic system? Adiabatic means there is no heat transfer. Okay, so to get adiabatic system, which means it has to be fully insulated, because across the boundary there shouldn't be any heat transfer between them. Okay, and also have to make sure the internal temperature is the same, so no temperature changes, of course. Only then there's no energy transfer. Sorry, there's no heat transfer. Okay, and what are the similarity of heat and work? Okay, first of all, heat and work are associated with process. It is not a state. Okay, from state 1 to state 2, we know that in between, this is what we call the process. And heat and work, or collectively we call it the energy. Okay, sorry, not U. U is internal energy. Collectively we call it energy, part of the total energy. It's really associated with the process itself, not to each of the state. Okay, so it's the energy change, the energy transfer, make the change in the state from 1 to 2 or 2 to 1, either way. Okay, so doesn't matter it's a heat or work, it's associated with the process, not to the state. Okay? So unlike property, heat and work has no meaning to a state. Pressure, temperature, velocity, volume, specific volume, they are property of a state. They only have meaning. They have meaning to a certain state. When we talk about heat energy in a state, there's not so much meaning about it. It's always the changes in the energy, the one that has meaning to us in thermodynamics. Okay, so for that reason, when we write the work or heat, we don't write in just one state. We always write it across a state. So the work from state 1 to state 2, or the other way around, work from state 2 to state 1. Okay. Heat from state 1 to state 2, or heat from state 2 to state 1. Okay. So 1 to 2 is the process A, basically. And it can also be this process B. So different process, the work and the heat involved might be different. Okay. So this is the state. In between, the line, the path, that's what we call the process. Okay, that's where the heat and the work actually matters. Okay, and also for property, we write it as like this. Okay, the changes in property. Okay, but for work, usually we just write like this. We don't write in change in the, because it's a difference. The work is already work 2 minus work 1 for this. Okay, so what we concern is this. Not saying that we don't write this way, okay, but usually it's this to this. Okay, so it's already not it's already a delta, so we don't write as delta like this. Then it's a delta of a delta. There's no meaning in that. Okay, so change in property we write in delta. For work, usually we just write as from one state to the other. Okay, because it's a path function. It's a process associated to a process. Okay, and of course I forgot to mention this. We have to look at the boundary. Okay, the boundary has to be certain in order for us to know whether there's a work transfer, whether there's a energy transfer. just like the candle earlier. If we look at the candle itself, there is an energy transfer, yes. Look at the A itself, there's energy transfer as well. But then look at the A plus the candle, there's actually nothing transfer outside the boundary. Electrical work, another form of work other than the kinetic energy, potential energy, right? So to get the electrical work, we usually calculate from the electrical power. I think this equation you should be more familiar than me. Okay, so the electrical power is the voltage multiplied with the current. Okay, but it's power, so therefore it's a rate of electrical energy. Okay, and for us to get the work, because this is rate, so therefore joule per second. So for us to get the joule, which means this we have to multiply with the time. Okay, so therefore we know the power. We need to know how long the electrical power is being supplied to a system. For instance, here, supplying to here for how long? Then we'll be able to calculate. So it's really just the power multiplied with the change of time. The time, basically, the machine is operating. So then we'll be able to get the total amount of energy being transferred to the system. Okay. If we take the example of the electrical motor just now, you're running at a certain voltage, running at a certain ampere, running at a certain time. So the total electrical energy, sorry, electrical work, okay, because there's no temperature difference in the process, assuming the electrical motor doesn't heat up, the reason they heat up is because there's losses, okay, not because the work you do is a heat transfer, okay, but the electrical work is really voltage time ampere time the time it is operating. Then you know how much total energy, total work being transferred into the electrical motor. So just a different work we calculate differently. For instance, the kinetic energy, mv squared over 2. So electrical work we calculate this way. And then there's also mechanical form of work, which something have to move. We push something, your car moving, so that kind of work. So for this, the work is really the force time distance. Okay, because something is moving. Okay, so if it's a shaft work, okay, still force time distance, except that because it's rotating, so now the distance that we're talking about is this point, you have to move to another point. So the total distance that it moves is the chord length S. Okay, so then we can roughly rearrange the equation. Okay, the force is really the torque over radius, because torque is force times radius, this one. Okay, so we just rearrange the equation. So force equal to torque over radius, and the chord length, the distance, circumference distance that the work has result in the displacement, is 2 pi r, which is the circumference. Okay, multiply with the rotational, how many rotation that it has went through. So then we rearrange everything. The shaft work is basically 2 pi nt. Okay, so just the equation after we rearrange it. And of course, if we look at the rotational, how many rotation we're talking about here? We're talking about how many rotational per time, over time, RPM, for instance, or RPS, revolution per second, or revolution per time, per minute. Then we get the power. It's a rate of energy. Okay, so the minute we plug in time, we plus the the factor of time, it becomes power. It's a rate of energy already. Okay. Other than the shaft work, there's also spring work as well. Like a spring, it goes to a different length. Okay, so this is more straightforward, force times the distance only. And in the spring, F equal to Kx, so then the spring work is basically this. Okay. So it's just a different equation to define different form of work. So this I can write as work in kinetic energy and then work in potential energy. There's another equation for it. So all these are just the different equation for different type of work. So very often we just remember it. Okay? So of course you can derive it following here, but most of the time we just remember it. Okay, right then. So now that we have looked at the microscopic, sorry, we have looked at the microscopic energy, which we, sorry, let me just go back to here. Okay, which consists of the molecular level. Okay, so collectively we just call it the internal energy. Okay, and then the electrical work, the kinetic energy, potential energy, everything. So all that are macroscopic form of energy. Okay, so there can be, and there can be heat, there can be work as well. Okay, so then it's quite important for us to revisit back the first law of thermodynamics. Okay, which basically means the energy cannot be destroyed. It can only transfer from one location to the other. Okay, so this, I think everyone seen the example before. Okay, so I'll focus on talking about the example below here. So the cooking of potato, you put heat in, so then the change in the, sorry, the energy of the potato, the value will change as well. It will increase. Okay, you cook a pot of water, there's a heat energy goes in. If there is a losses, then the changes in the energy in the water is not as much. Otherwise, 15 kilojoule go in, the energy in the water should change by 15. But because 3 of them goes out in terms of heat loss, so then the total energy change here is only 12. So it's always balanced because energy cannot be destroyed. Okay. Likewise, if it's heating up adiabatic, which means there is no heat transfer across the chamber, you're doing 5 kilojoule of electrical work to the space inside the chamber, then the internal energy should increase by 5 kilojoule. Okay. Same with this. If it's adiabatic, of course. If there is a changes, this is not equal to 0, then this will not be 5, maybe 4, because 1 kilojoule maybe go out from there. Okay, or it might goes in. If it goes in, sorry, if it goes out by 1 kilojoule, then this will be 4 kilojoule. Of course, you have to balance. But if it's the other way around, 1 kilojoule go in, here goes in another 5 kilojoule, then total here will be 6 instead of 5. Okay, so it's always balanced. We'll look at the equation in a minute. Okay, same goes for this and same goes for this. Okay, even the piston pressing a closed cylinder. Okay, 10 megajoules of work done to the piston here. So the fluid inside here will gain the energy of 10 kilojoule. Okay. So what is important here really is that energy has to be conserved. Okay, so therefore we have the energy balance equation. Says that the total energy entering the system minus the total energy leaving the system must equal to the changes in the total energy in the system. Okay, so the changes must be the net, the imbalance between the in and the out. Okay, and mathematically, this is how we write out. Okay, so E in minus E out, energy in minus energy out, always equal to the change in the energy in the system. Okay, but E is the total of micro plus macro energy, if you remember the definition earlier. And micro energy, we call it the internal energy. Okay, so therefore, we can also write this as this term. This is the micro, this is the macro. Okay. But of course, not all the time the system has kinetic energy and potential energy. So therefore, a more relevant equation to us, following the same definition still. Okay. So the change in the energy in the system, okay, which is E in equal to E out. Okay. Sorry, E in minus E out. Okay. So that equal to this. Okay. Pretty simple. You can break into three parts. Okay. This is for the heat. This is for the work. This is for the mass flow. Okay. The three of these. Okay. In the first closed system that we're going to look at, there is no mass flow exchange. So this part will be zero. So our equation is only these two, basically. Okay. So what it says is the change in the energy in the system. I should take this as an example. Okay. Is equal to the difference between the in and out heat plus the difference between the in and out work. Okay, so it's an energy balance only, really. If there is a mass exchange like this here, then of course not just the work, not just the heat, also have to look at the imbalance between the mass in and mass out. Okay, so this is really the energy balance equation that is more concerning to us. Okay. So before going into the example, any questions so far by anyone? Anything not clear? I do understand it's very theoretical. Maybe after you listen to it, it feels like you sort of understand, but still sort of confusing. There's always a feeling of that when we look at the theoretical part of any subject. Okay? So probably let's look at the example, then you can better relate what you have heard earlier. Okay, but in the meantime, if there's any question, feel free to ask as well. Okay, I'll try my best to explain. Okay, so let's look at this example here. Okay, so it's a cooling of a hot fluid in a tank. Okay, so the tank is hot at the beginning, and then there's a fan trying to cool it down. Okay, so here the question say a rigid tank containing hot fluid that is cool while being stirred by a paddle wheel, this paddle wheel. So this paddle wheel will stir the fluid inside for it to cool down. Okay. Initially, the internal energy of the fluid is 800 kilojoule. Okay. And during the cooling process, the fluid lost 500 kilojoule of heat. It's losing. So this heat is going out. It's negative. Okay. And paddle wheel does 100 kilojoule of work to the fluid because it's stirring it. So therefore, there's a work going into the system. For work going into the system, they are negative as well. Okay. So the question wants us to determine the final internal energy in the working fluid, which is how much is this? Okay. So there is a important, you can, when you look through the example like this, okay, you always notice that the first thing is assumption, because in engineering field, there's always assumption that we are making. Okay. So in this case, the most important assumption is there is no changes in the kinetic and potential energy in the system. Because number one, the system is not being raised to a higher altitude. Second, it is not moving. Velocity is zero. So therefore, there's no kinetic energy, there's no potential energy in the system. So we don't have to consider them. Okay. And because of that, if you remember, sorry, E equal to U, internal energy, plus kinetic energy, plus potential energy. Okay. So when this is zero, this is zero, so E equal to U. Okay. So which means our equation, this equation, okay. So this part here, delta E, basically equal to delta U. Okay. And this part here basically is Q, let me just see back here, Q in minus Q out plus Q in W minus Q out. Okay. So Q in minus Q out plus W in minus W out. Okay. It should have plus the E mass in, mass out. Okay. I'll write it in full. This is 0, 0. Okay. And then this is a closed system. Because it's closed system, so this is 0 as well. Okay. So then you in this system here, okay, there is no Q in, there is a Q out, yes. Okay. There is a shaft work in, okay, and then there's no shaft work, sorry, there's no work out. There's work in, there's no work out. Okay. So then it reduced to this, basically. Okay, so that's how we get to here. So the work in minus the heat go out must equal to the change in the internal energy, which is U2 minus U1. U1 we already know. So then U2 we can find out just like that. Okay. And when you plug the value into this equation here, you don't have to look at the sign anymore, okay? Because the minus here is already taking into account the negative in the process, okay? So that's how you can find out the internal energy in the second state. So state 1, U equal to 800 kilojoule. Going into the state number 2, U2 is, you find out will be 400 kilojoule. So in the process from 1 to 2, okay, there is a energy go out by this much, and then there's a work go into the system, 100 kilojoule. Okay, so that makes the state changing from this internal energy into this internal energy. Okay, so that's what this example is trying to demonstrate, how we're using the energy balance equation. Okay, and think quickly going into the, I think not many left, so let's finish covering this part here, then we'll take a short break. So next, let's look at moving boundary work. Okay, so one example of moving boundary work is the engine in our car. Okay, because that's basically piston. So as a piston, the pressure in the cylinder expand, it pushes the piston moving. So the boundary is moving. The piston from a small volume, okay, going into a big volume. So in the process, there's a work done by whatever fluid inside the cylinder. Okay, so because the boundary is actually changing, noticeably changing, so therefore this is a boundary, moving boundary work, basically. Okay. So in a way, it's a piston. You can understand that way. Okay, maybe it's easier to understand by looking at this. Okay, so for moving boundary work is really just another type of work, which we write it as pressure multiplied with the change in volume. Okay, remember just now we have many different type of work, which the equation is different. For moving boundary work, then it's P V2 minus V1. The change in the volume under this pressure is what result in the work. Okay, we write as WB basically. And associate with the expansion and compression. Obviously, expansion is a positive work. The volume is doing, the boundary is doing work. The system is doing work, sorry. And compression is the other way around. Work is being applied to the system. Okay. Okay. And if you remember quasi-equilibrium process, okay, in real life, well, this happened very fast. This is not really quasi-equilibrium, but in our analysis, most of the time we assume it to be quasi-equilibrium, which means the pressure is uniform throughout the fluid, of course, temperature is uniform, the substance is uniform, everything is uniform, therefore it's quasi-equilibrium process. Okay. Okay, moving boundary work. Okay, this is a bit more theoretical. Probably don't need to go so detailed into it. Okay, so this is a definition of it, generalized boundary work relationship. So it's the pressure multiplied with the volume. Okay, so there are a few examples here. Okay, so you can have a look later on. I will just briefly go through what they are. Okay, so when it comes to system, okay, it can be isochronic, which means the volume is constant. So work can be done under this different condition. Okay, so when the volume is constant, it's an isochronic process. Okay, so you can see on the PV diagram, V1 equal to V2. So the change in pressure. Okay, so in this case, if we're talking about the boundary, the boundary work, because the boundary doesn't move, volume doesn't change. So therefore, this will be 0. So there is no boundary work in the process, in isochronic process. Okay. On the other hand, isobaric is basically P equal to constant. Pressure is constant. Okay. So on the PV diagram, you can see from 1 to 2 is a constant pressure. Okay. So for constant pressure process, the boundary work is literally pressure multiplied with the change in the volume from state 1 to state 2. If state 2 is larger than state 1, which means expansion, so therefore you get a positive work. If state 2 is smaller than state 1, you get negative, which means you compress it, and therefore it is a negative work. Okay, and because volume, we can express in specific volume as well. So therefore, the equation can be in this term as well. Okay, this is in the specific volume term, multiply with the mass at the front, of course. This is not specific work. This is the total work. If we take WB over mass, of course, we can get the small cap WB, specific boundary work. It's not a problem as well. So then that will become V2 minus V1. Okay, so really this B, we should write as 1, 2. Sorry, 1, 2. The boundary work from state 1 to state 2. That's how usually we write it. Okay, so this is isobaric constant pressure process. And then isothermal process, which means temperature equal to constant. Okay, so for this, no problem. The boundary work from state 1 to state 2, there is a P1, there's a V1, there's a P2, there's a V2. Okay, so you can see how it can be derived here. Okay, so it's not as straightforward. So eventually you get to this. Okay, so depending on the type of process, the boundary work is always P dV from 1 to 2. Okay, if it's a isobaric process, there's a constant pressure, then we can reduce to this equation, much easier. But otherwise, the integration itself will bring you to a slightly different equation that we should be using, okay, rather than P1 V1. Okay, it's not like this. Okay, we have to plug into the integration here for us to find out what's the equation for the work, the boundary work in the isothermal process. Okay. Other than that, there's also another process that you should know as well, which is called the polytronic process. Okay, polytronic process basically means PV. This equation here, P multiplied with volume to the power of n. Okay, is a constant. Okay. So there is it's a, you can think it like a very generic way of expressing the isothermal isobaric process earlier, because depending on the exponent n, is a different type of process. When n equal to 0, it's a constant pressure process. When n equal to 1, it's a constant temperature isothermal process. Is n equal to infinity, then it's a constant volume. I think it's opposite. Sorry, these two are messed up. Okay, do take note. There's a mistake here. When n is infinity, of course V is very big. T is almost negligible. So it's a constant volume. Okay. When n is ratio of specific heat, which we'll look at specific heat later on, okay, then it's an isentropic process. Isentropic process means there's no losses. Okay. It's a very ideal condition, but then there's no losses in between. Okay. So either is a isobaric, isothermal, or isenchronic or isentropic process. They are all polytropic process. It's a very general way of expressing the process. PV to the exponent of n. Okay. Right then. So I think that's pretty much about the theory of energy and energy transfer. Okay. So moving to the chapter 4, we'll be looking at I think specifically on the yes, we'll be looking at the energy balance for a closed system. So then we'll be looking at more calculation and more example. Then it'll be probably easier to relate what you learned just now with how to apply it in the system level. Okay, right. So I think all the theory part has make you feel bored already. Some of you probably already sleeping. Perfectly understandable. So why don't we take like a 10 minutes, 10 of I think we have time. So let's say maybe 10 minutes breaks. Okay. Now it's about 3:40. So let's say we come back by 3:50, and we'll continue on this chapter 4. Okay. So 10 minutes break. We'll come back by 3:50. Okay, right then. Let's continue into the next chapter. Okay, you all can see the screen, right? Everyone can see the screen. Yeah, okay. Right then. So this chapter will apply the energy balance that we already looked at in chapter 3 in a closed system. Okay. And more specifically, we'll be looking at two type of system that run on pure substance and system run on ideal gas, since we learned both before this. Okay, so we'll first look at how we can analyze the closed system running with consist because there's no mass exchange, so it's not running. So it's a closed system of a pure substance, and then we're looking at closed system of a ideal gas. Okay. So what you will learn out from this chapter here is, of course, applying the first law of thermodynamics. Okay, the conservation of energy, basically, energy balance, in other words. Okay, for the closed system. Okay, and you'll be applying. Okay, same thing. It's repeating. Okay, and then, of course, in order to do so, you have to describe the internal energy, enthalpy, and specific heat of ideal gas. So this is for ideal gas. Okay, for the pure substance, you'll be also describing the internal energy and enthalpy of the system. Okay, so we already looked at this, so I don't have to go through that again. Energy cannot be destroyed um, or created. Okay, and then we did look at this. Okay, so I think it's easier that we look at this rather than go through more equation, which might be confusing for you. Okay, so the energy balance of a closed system undergo a cycle. Okay, to put it simple, okay, the work in minus work out plus the work in minus work out will be equal to 0. Okay, this is, of course, when there is no change of internal energy. Okay, or maybe I should say there is no change in total energy, which the total energy we know is a change in internal energy plus change in kinetic energy plus change in potential energy. So assuming there's no elevation change, assuming the system is not moving, so this is definitely 0. So in a closed system, they undergo cycle, which means it just keep going. Okay, so the loop goes like this. It's not one way only. One way, of course, there is changes, but then when it go backward, maybe I should draw like this, it'll be easier to understand. From state 1 to state 2, 1 to 2, there is a change in energy, yes. And then from 2 to 1, there's a change in energy as well, which they'll balance back. So therefore equal to 0. Okay, provided there is no losses. That's very important. We don't consider losses in our analysis here. Okay, and this is summation of Q. This summation of work. Supposedly there's a E mass in minus E mass out as well. Okay, the full equation. But because this is a closed system, so this is 0 as well. So then we live with this equation here. Okay, so that basically got to say, if we call the difference between Q in and Q out as a net energy, sorry, net heat, okay, and work in minus work out equal to net work. Okay, the net of heat and the net of the work, then they will always balance. Okay, so this is what happened in a closed system that undergo cycle. Very important, cycle. If it's not cycle, this will not be 0. Okay, so let's look at an example. Okay, so this example here, okay, a piston cylinder device is a very long solution. Okay, we go back slowly. Okay, so a piston device containing 25 grams of saturated water vapor. Okay, so we start with a system with a pure substance. Okay, so it's a saturated vapor, water vapor, which means the quality is 1, if you remember the pure substance. Okay, it can be mixture, it can be saturated liquid, it can be saturated vapor. In this case, this is a saturated vapor. Okay, it's maintained at a constant pressure of 300 kilopascal. So pressure is constant. Okay, a resistant heater within the cylinder is turned on and pass a current of 0.2 ampere for 5 minutes from a 120-volt source. The textbook was from US, so therefore the voltage is 120. If it's in Malaysia here, it should be 240. Okay, which means there's electrical work going into the system. Okay, and at the same time, a heat loss of 3.7 kilojoule occur. Okay, so show that for a closed system, the boundary work and the change in the internal energy can be combined into a term called delta H, which is the change in the enthalpy. Okay, that's the first question. Okay, and second, determine the final temperature of the steam, which means the saturated water, because of the heating by the resistant heating heater, it will turn into steam at this constant pressure. Okay, so important assumption here again, kinetic energy and potential energy are 0. Okay, because the system is not being elevated to higher elevation, and it's not moving either. So potential energy 0, kinetic energy also 0. So whatever changes in the energy in the system basically equal to the changes in the internal energy. Okay, so it basically looks like this, the system. Okay, it's a piston cylinder device. Okay, heat up by this electrical work. Okay, this is the initial state. Well, this is the initial state. Okay, this is the state after it's being heated up, and in the process there's a heat loss. This heat loss, and therefore it's a Q. This is work in, basically. Okay, and it starts from saturated vapor and then go to superheated. Okay, if you remember, the constant temperature line goes like this. Constant temperature line. Okay, So obviously 1 to 2 is not a constant temperature, okay, but it's a constant pressure. So first, let's prove that the boundary work and the change in the internal energy can be combined into a term, delta H. Okay, so let's look at the solution here. So the change in the system equal to energy in minus energy out. Okay, so this delta E, okay, supposedly equal to, sorry, plus potential energy, but because it's 0, so therefore this part is quite easily understand. Okay, we look at the right hand term first. Okay, and the change in the internal energy is basically from state 2 to state 1. Internal energy in state 2 to state 1. Okay, so there's a U2, there's a U1. Okay. And then we have the front part. Okay, so the front part, of course, we can expand it, but then here, just make it simple. Okay, we have a Q involved, we have a work involved as well. Okay, so Q is a heat loss. Okay, the work we divide into 2. Okay, one is a boundary work, one is the other type of work. Okay, so for the boundary work, we define it as pressure multiplied with the change in the volume. Okay, so then the equation become like this. Okay, and because it's constant pressure, so then we can expand the equation to become like this. Just this part here. Sorry, let me draw it nicely. So this part here, it become like this. We can expand it. Sorry, we move this to here. What am I saying? Okay. So then we have Q minus any other work done to the system. Okay. Which in this case, this other work is basically the electrical work. If you didn't notice, right? Because this is the other work that go in. What happens is when you heat up, for it to maintain constant pressure, this boundary will start to move because you expand, you heat up. Okay, so really there are 2 work involved here and 1 Q involved. Okay. So then the right hand term, this one that will expand. So the U plus PV, that is what we can combine and call it the H2. This is H1. Okay. So internal energy plus boundary work that basically equal to the enthalpy. Okay. So then the first part is completed. Okay. That's the derivation only, really. So enthalpy is a H, or in the specific term, the small h, which is the another column, if you remember, in the property table. Right? This is the property table for refrigerant. If you notice that specific volume, internal energy, enthalpy, and entropy. Right? Entropy, we're not looking at it because that is for the advanced thermodynamic. Okay. So specific volume, I think you all know already. Internal energy, now you know better. It's basically the sum of all the microscopic energy. And then enthalpy is basically U plus PV. Okay, it defines the energy level as well, really. Okay, of the system. Okay. So then next, the question wants us to find out the final temperature in the system. Okay. Since the pressure is constant, okay, so then temperature will show increase. So then it's really just a matter of solving this equation that we have derived. Okay. So first, let's find out the electrical work so that we can solve this. We have Q. Yes, we need the work, the electrical work. Okay. So for electrical work, the equation is really voltage times ampere times the time. Voltage is 120 volt, ampere 0.2. Time, don't forget this, you get joule per second. So the time, you want it in second as well. So 5 minutes, you have the time 60 seconds, you get 300 seconds. So from there, you get 7.2 kilojoule or 7,200 joule. Usually I'll just keep it in SI unit. Sorry, in the base unit, so I don't confuse myself. Okay. So now that we know this, okay? So then we have to find the state of the steam in order for us to know the temperature. Okay. So first of all, we can approach that by finding the enthalpy at the first state. Since we know the first state is saturated vapor, we know that this is the pressure. Okay. So then we look at the saturated table for this pressure, and then you'll find out that the Hg is this value. Okay. Very simple. This H1 equal to Hg, because this is a saturated vapor, basically. Okay, so then you have this value. So then we can substitute into the equation here. Okay, we plug this in, Okay, the mass, we know the value, the question already gives us. So this, we just find out. So then we should be able to find out the specific enthalpy at state number 2. This is at state 2, hence the H2. Okay, so now that we know the specific enthalpy at H2, then we can refer to the superheated table. Okay, or table A6 in your textbook. Okay, so in this case, I strongly suggest you to, I think I did put it in the share folder. Okay, so refer to the textbook. You have the superheated table for water. This is a water problem, right? Yes, this is steam, saturated water vapor. Okay, so now it becomes superheated. So then you just have to look at the pressure, this pressure, and then find out for this enthalpy value, how much is the temperature. Okay, so obviously you need to know how to read the thermodynamic table by now. Okay, but this is how we find out the second state of the flow of the system. Okay, and then from there we should be able to find out how much is temperature. Okay, so I'll leave you to try this later on as an exercise. Okay, so please go find out the superheated table and then try to read this temperature based on this pressure and this enthalpy. Okay, so what it says is it will go to another temperature, that's for sure, because this is another temperature line. This is T1. Okay. So that's the first example there. Okay. Second example, okay, let's do another one. And then there is one breakout session. So this one, I will leave you to try yourself since solutions are all given already. Okay, so let's go through another example, how we can use the energy balance to actual system problem, I would say. Okay, so this here is it's called the unrestrained expansion of water. Okay, so what it has here is a rigid tank. Okay, it's divided into two equal parts. Okay, so it's a solid tank, which means this is a system boundary. Okay, solid, which means it doesn't expand. So which means the system boundary doesn't go beyond here. Okay, and it's divided into equal part. Okay, so 50% of the volume, 50% of the volume. Okay, so one side contains 5 kg of water at 200 kilopascal and this temperature. This amount of water, this pressure, this temperature initially. Okay, the other part is evacuated. It's a vacuum basically. Okay, and then the partition is removed. Initially, there's a partition, and then someone remove it. So what happened is this H2O will try to go to that side. Okay, but in a way of expansion. So it expand to the entire tank. Okay, and the water is allowed to exchange the heat with the surrounding, so that the temperature remain at 25 degrees Celsius. It says go to the initial value. That basically means temperature is constant, 25 degrees Celsius. Because when expand, you cool down. But in order to maintain it, so therefore there is a heat input. Okay. So the question wants us to determine A, the volume of the tank. How much is total volume of that solid tank? Okay, and B, the final pressure. Temperature is the same, but then now it expands, so how much is the pressure? Okay, and the heat transfer for this process, which means Q then. How much heat has to be transferred into a system for it to maintain at this temperature due to this expansion. Okay, so the solution here, again, the assumption, kinetic energy, potential energy equal to 0. Okay, so delta E equal to delta U. If they are not 0, then it has to be taken into account. Okay, but most of the example you see, we analyze on the system that is not moving and it's not being raised to a higher elevation. So kinetic energy and potential energy always, most of the time I would say, we assume it to be 0. Okay, but not all the time. So first, let's find out the volume of the tank. Okay, so how can we do it? Sorry. So first of all, we know the initial state. Okay, the initial state is it contains water, so which means saturated liquid. It's a compressed liquid, more accurately say, it's not saturated. Sorry. Okay, but we have the pressure, we have the temperature. Okay, so then we can approximate the specific volume. Sorry, just a minute. Okay, Well, we learned this in chapter 2, I believe. Okay. For compressed liquid, we can either referring to the compressed liquid table, okay, or within reasonable accuracy, in fact, we can assume it to be saturated liquid. Okay, so in this case, we'll use the easier option, which is to assume it to be saturated liquid. So at this temperature, initial temperature of 25 degrees Celsius. Equally, we can refer to the pressure, okay? But since temperature is constant here, so let's refer to the temperature, much easier. So then, this is water, H2O, don't forget. So we are referring to the thermodynamic tables of water. Then you'll be able to find out the specific volume, which is 0.01 meter cube per kg. Okay? And you know, initially there's 5 kg of it. So then if you multiply with 5 kg, this is the mass, this is a specific volume at state number 1, then you can find out the actual volume in state number 1, which is 0.05 meter cube. Which means, sorry, here, this is 0.005 meter cube. And since the cylinder is equally divided initially, so which means this here should be 0.005 meter cube as well. So the total will be 0.01 meter cube. That is the volume of the tank. Okay, so that's how we can get the volume of the tank in this case. So that is done. Second, the question wants us to find out the final pressure in the tank. Okay, after the separator is being removed, pressure expand, we add the heat, there's heat transfer into the tank. So we maintain the temperature at 25 degrees Celsius. So how much will be the final pressure? Okay. So then, once we know the volume of the second state, which is V2, 0.01 just now, okay? So we can find out the specific volume, which is 0.002, okay? The reason we want to find that is because we're not sure whether after it expands, are they still compressed liquid, or it's a mixture, or it turns super heated completely. So first we have to determine the state of the substance first. Okay, so we know the one property at state 2, so that should allow us to determine the quality of the substance. Okay, so if we look at because it's constant temperature, we look at the constant temperature, the specific volume for saturated liquid will be this value, and the specific volume for saturated vapor will be this value. Okay, very simple. This is the temperature equal to 25 degrees Celsius line. Okay, so this is VF, this is VG. Okay, and our V2 is somewhere here. So therefore, it's a mixture, that's for sure. Okay, because VF is this value, VG is this value, and it's in between. This number is in between here. So if we need to find out the quality of the mixture, we can actually. The vapor fraction. Okay, so it's just a matter of V2 minus VF over VFG. Okay. But that's not what we are looking for at this time. Okay, what we want is the pressure of the second. This is P1. So we want to know how much is a P2 because it's saturated, it's mixture. So it's much easier. We just have to refer to this saturated pressure line for this temperature, which according to the table, you should find out that this is the saturated pressure. So this is the the mixture pressure at state number 2. Okay, so that's how we find out the pressure next. If it's still compressed liquid, okay, if it's still compressed liquid, let's say it only goes from here to here. Okay, we have V1, we have V2. Okay, so then in that case, you can make this assumption to find out the pressure. Okay, so we need to know for this V2 value, because it is compressed liquid. Okay, so we can assume that the V is equal to the saturated liquid value at what pressure. So then we can find out from here. Okay, so depending on what state what phase, sorry, the liquid, the substance is, then we can find the pressure accordingly. Okay. And then the last part is to determine the heat transfer in the process. Okay, so for this, definitely we have to use the energy balance equation. Okay, so for the energy balance equation, this here we know is equal to change in the internal energy. So therefore, mass multiplied with the specific energy change from state 1 to state 2. So therefore, U2 minus U1. Okay, and the net energy transfer, E in minus E out, okay, should be Q in minus Q out plus work in minus work out. Okay, there is Q in. What about work out? Okay. In this case, there is no work going out at all. It's just an expansion. Okay, so this is O0. So therefore, you end up with only Q. Okay, so this is what we're going to find. The mass, we have it, 5 kg. U1, we also have it. We do. U1 is... Oh, we don't actually have U1. Okay, but U1 we can find as well. U1 is basically UF at 25 degrees Celsius. Okay, so it's something that we can find out quite easily. Okay, the problem is U2. So to find U2, well, we have to find out the quality first, because U2 is a mixture. So therefore, it should be UF plus the quality multiplied with UFG. The quality, like how we established just now, can be calculated based on the specific volume, because we know that's how we determine it's a vapor. Okay. In fact, yes, exactly. This is what it is doing here. Okay, so once you have U2, plug it in, then you will be able to find out how much is the Q. That is the energy, the heat, sorry, have to transfer into the system to maintain it at this temperature so that the second state actually is here and not somewhere else. Okay, so in the end of the day, you should be able to find out how much is the Q, the heat transfer into the system. Okay, so really, if you look at these two examples, I'll just draw here. Okay, so it's really from one state changing to another state. Okay, it can go this way, it can go up, it can go the other side, doesn't matter. Generally, we just draw it like this. Okay, from state 1 to state 2. So really, state 1, the property that define it can be pressure, temperature, specific volume, specific energy, internal enthalpy. Okay, you need property to define state, remember. Okay, and for state number 2, you also will have the corresponding property. Between them, okay, is what define, is there any Q, any work? Okay, and to govern this, really, we have to use the energy equation, the energy balance, which is in minus E out equal to change in total energy. Okay, so the problem is always surrounding finding this property, finding this property eventually, right? And very often we need this information to complete it because it's this process that change from state 1 to state 2. Okay, so this is basically how the thermodynamics problem, the question will look like. In fact, this is how in real life we solve the thermodynamics problem as well. It's always about finding the property at a new state. Or from there, to find the property of a new state using the known energy changes in the process, or the other way around, from the known state number 2, go back and find how much is the energy involved in the process. Okay, it can be the other way around as well, no problem. Okay, but it's always like this, the interrelationship between them. Okay, right. So here are the two examples on a pure substance. Okay, how we can solve it. If it's an isentropic, it's an ideal gas, then it's just a matter how we determine the property. The relationship between the energy balance still the same, basically. Okay. And for this example here, well, this is a refrigerant R134. Okay, so for this, I will leave it to you to try. Okay, after this, there's a step-by-step solution as well, so you can cross-check it. Okay, follow the example, try it, and then try without looking at the solution. Try to solve one time. Okay. Right, moving on, because there are quite a bit that we need to cover still. Okay. Okay. So next, before that, any question on the two examples so far? Does that give a clearer idea? How do we use the energy balance in solving the problem?
Doctor, I have a question.
Yeah.
For example 1, it states that it's a quasi-equilibrium process,
Mhm.
then the work is done by the system. What does that mean? Because electrical energy is the work done to the system. Why is done by the system?
Done by the system.
Yeah, there's the explanation at the analysis part. It says the work to be done by the system. What work done by a system?
In this one?
Yeah, this one, this one.
It just means that W is the work, in general, W is the work done by the system. So for work, electrical work, so therefore it's a negative because it's a work going in to the system. So work E plus work E, this is the total work done by the system. This is positive, it is actually done by it. This is negative, it's taking energy from outside.
Then at the B part, the WE is positive for the B.
The B should be negative. B should be positive, yes.
Yeah, for the B part, WE in is positive.
E is negative and B should be positive because the arrow going out is a positive work. This is going in, negative work.
I mean, for the B part, the question B, it states that for the calculation part for the right side, that one it says that WE in is positive. So
WE in is positive. Hang on, yeah.
yeah,
E is others. Oh, because it's already minus. You already minus it. So hang on. Okay. Okay. Maybe I'll let me re-standardize the way it's being writing. Okay. So if like this, then only we have to look at the positive or negative of the work. Okay, so work out will be in will be positive, out will be negative. Okay, but when they write in this way, already minus, actually, sorry, my bad. I should have said that it shouldn't need to. Because this out will be negative already. Okay, so when using this here, this one here, then really just look at whether it's in or out. Just plug it in. Don't have to apply additional negative or positive. Which is, I think, the case here. So forget about the positive, negative. Okay. If the solution here is using that Q in minus Q out plus work in minus work out equal to delta E. Okay, so then this Q out, Q out will be here. This work W will be this one, and WE should be this one. Is that the case?
Understand.
I don't quite think it is though. This. Okay. I'm not too sure about this. Later on, you check whether it's consistent or not. But if I'm going to solve it, I will solve it this way. Okay. So I will just follow here, and then I'll follow the step. Okay? But the sign convention usually in out. If you already minus like this, then you just take the magnitude right away, because the minus is already taken out the direction. And sorry, the other question you were asking just now?
Yeah, the WE in is positive instead of negative because it's done to the system.
Yeah. I think follow this might be better. So you don't have to think about whether it's a doing or done.
Okay, understand. Thank you.
Okay. Okay. Anyone else have a question? Okay, right. If no, then we'll move into the next part, which is ideal gas, basically. Okay. In fact, before ideal gas, let's look at what is specific heat. Okay. So specific heat is basically the energy required to raise the temperature of a 1 unit of mass of substance by 1 degree. Okay, so naturally, the unit of it is joule per kg per Kelvin or degree Celsius, because the energy required to raise 1 kg of a substance, the temperature by 1 degree Celsius or 1 Kelvin, because we're talking about delta T equal to 1 Kelvin, which is 1 degree Celsius as well. Okay, and specific heat is a property of a substance. Different substance has different property. Sorry, what am I saying? Of course, they have different property. Different substance has different specific heat. Okay, and specific heat can be defined by constant volume specific heat and constant pressure specific heat. Okay, because under constant volume and under constant pressure, if the volume is changing, the heat required to heat up 1 degree Celsius of 1 kg of that substance, it can be different. Okay, and different material are different. Okay, here you can see roughly the scale for different type of substance, different types of material. Okay, there's water, there's liquid, and then there is also solid. In this case, you can see the scale can be very different. Okay? So in practice, for us to find out number, we just need to look out for the property, and then we know the number. Okay. It applies to not just the ideal gas, but also to any substance, basically, even pure substance. If it's not pure, that's where the controversy can come, because you need to mix them together. But in our case, we always work with pure substance, so it's relatively easier to estimate a number. If you mix these this amount of part of water and this amount part of steel in a water bath, let's say, then the CP, the specific heat basically is by mass. You can estimate that as well. And also going to lighter gas, like paper and everything, air, CO2, hydrogen, everything, the number will be even, of course, doesn't go here because it's 0. They will go even lower. Okay, so these are the different type of gases usually. Okay, so the unit of a specific heat is joule per kilogram degree Celsius or joule per kilogram Kelvin. Okay, it can be kilo as well, no problem. Okay, it can be mega as well if it's a unit is very large, but most of the time it's kilojoule. So number ends up around 1 point something, 10 point something. It's not too high like this. Okay, and sometimes the specific heat can be given in a molar basis as well, per molar mass. Per molar mass, not necessarily per kg mass. Okay, so in that case, just have to pay attention to the value given. But for practice, most of the time we use kg, much easier. Okay. And for ideal gas, okay, someone has proven that. In fact, just now we have seen the example. The enthalpy is basically the internal energy plus the boundary work, P multiplied with V, pressure multiplied with volume. Okay, and because PV equal to RT in the ideal gas, so therefore H equal to internal energy plus RT. Okay, so then the change in internal energy in an ideal gas, okay, in an ideal gas, we can approximate by CV multiplied with delta T. Okay, this is where the specific heat is useful for ideal gas. In pure substance, we can't. To find the change in internal energy, we have to do like earlier just now. We have to refer to property table, look at how the property change from state 1 to state 2. Only then we can find out the change in the internal energy. Okay, but for ideal gas, we can approximate. Okay, this is approximate. Approximate with acceptable error that the change in the internal energy is equal to CV multiplied with the delta T. Okay, and the change in enthalpy, this is internal energy. For enthalpy is Cp multiplied with delta T. Cp is the constant pressure specific heat. V is a constant volume. Okay, both are approximation, but then it's generally acceptable because the error is relatively small enough, as long as they are ideal gas. Okay. And here, well, we just say what I say. Okay, it's a simplified way to estimate the change in internal energy and enthalpy. Okay, and the relationship between Cp and Cv. Okay, Cp basically equal to Cv plus the gas constant R. Okay, if you remember what the gas constant R is, we learned that in the first chapter. This is how they relate to one another. Okay, and the ratio between Cp and Cv, that's what we call it the ratio, specific heat ratio. Okay. Usually Cp and Cv, the value will change slightly with temperature, even for ideal gas. For pure substance, definitely will not be the same at different temperature. But for ideal gas, sometimes the temperature play a role in the value in CP and CV. Okay, because as the temperature of the substance become larger, if it's ideal gas, of course, it's gas. So then the molecule will be further apart. So to heat up 1 kilogram of the mass, now it might be lower, it might be higher, the CP value. Okay, so it will not be the same exactly. Okay, right then. So let's try to look at one example. Okay. Yep. I think one example, and then I'll leave you with the other 3, which you can go through that, I think, quite easily. Okay. So this example here, okay, it is regarding the ideal gas. Okay. And it also include the energy balance as well. So it's basically analyzing the energy balance of ideal gas in a closed system. Okay, just now was pure substance. So now here is a ideal gas basically. Okay, so in this example here, argon is a type of gas which is very light, so it behaves like an ideal gas basically. Okay, and it's compressed in a polytropic process. Okay, polytropic process is this, as we've seen just now, with an exponent n, and the exponent given is a 1.2. Okay, and from pressure 120 kilopascal and 10 degrees Celsius, we compress it to 800 kilopascal. Okay, in a piston device. So P1, this is state 1. P1, sorry, I should just use here. Okay. State 1, P 120 kilopascal, temperature 10 degrees Celsius. To make it easier, change it to Kelvin. Okay, because the equation sometimes use Kelvin to calculate. Okay, and then it's being compressed to 800 kilopascal. Okay, so the question wants us to determine the work and the heat during the compression process, the heat transfer. Okay, so before we proceed, because it's ideal gas, okay, so let's find out the property of argon. So we have these 2 properties. The gas constant of argon, because it's ideal gas, we're going to use that later on. Okay, and also the CV of argon gas, which you can refer to, I think, the thermodynamic property in the textbook as well. Okay, gas constant is constant as long as it's argon is the same, doesn't matter of temperature or pressure. Okay, but for CV, no, it's given in a range of temperature. So under 300 Kelvin, which this case is, then the CV is this value. Okay. So then let's look at the energy balance equation. Okay, so energy balance equation still the same. The change in the system, delta E, because kinetic energy and potential energy, they are both 0. Okay, and then this here is really Q in minus Q out plus work in minus work out. Okay, there is no work out, okay, because work doesn't okay, sorry. The question wants us to find out the work produced and also the heat transfer. So we keep the work produced and then the heat being transferred. So assuming there's a Q in and then there's a work being produced, which is the work out. Okay. There's no work in here, so we keep these two first. Okay. So from here, the internal energy, because it's ideal gas, so therefore is mass multiplied with CV multiplied with the temperature change, T1 to T2. Okay. This mass we can bring over to make it a specific term to make the calculation easier, because otherwise we need to know how much is the mass. Okay, so by normalize it, we get the specific heat, specific work. Then there's no need for us to worry about how much is the mass of the argon. That's overall. We don't have the information anyway. Okay. So then the question will be how much, what is the property of state 1 and state 2? That's what we need to find out. Okay. For state 1, we have the pressure, we have the temperature. So therefore, we can find out the specific volume of the argon using ideal gas equation, PV equal to RT. Okay, because it's ideal gas again. So then we find out specific volume for the first state. Okay. Second state, we only have the pressure, but we can relate the pressure and volume through the polytropic equation. Okay. So we have to first change it to specific term first, which we can cancel out the mass because the mass always the same. Is within the closed system. There's no mass exchange. Okay. So then by just doing that, we will be able to find out the specific volume in the second state. Okay. So we have P1, we have T1, we have V1. So now we have P2, we have V2. So then we can apply this ideal gas relationship as well to find out that the P2 is how much. Okay. So then we have a complete full state of a property. P1, T1, V1. This is state 1. Now it goes to P2, T2, V2. Okay, state number 2. So that basically allows us to find out this right-hand side of the equation. Okay, then from there we can calculate this. Okay. So then the next one is to calculate how much is the work out. Okay. In fact, not the work out, the boundary work. Okay. So the boundary work, okay, we know that is in the pure substance is P. Sorry, no. The boundary work, okay, is actually P dV. Okay. But in this case, it's not a constant pressure. So we cannot just take as this. Okay, because the pressure is definitely changing. This is an isothermal process. Okay. So for isothermal process, for ideal gas, this is the equation. Okay. There's a derivation of it, but I don't remember, to be honest. So if you're interested, you can find it out. But for iso, this is not even isothermal. Sorry, this is a polytropic process. It's not isothermal. It's not isobaric. It's not isochronic. Anyway, so then the boundary work is really defined by equation like this. Okay, so which means we most of the time we just use it again. Okay, so n is here depending on the polytropic and exponent. So then plug in the temperature, we're able to find out this. Okay, and you notice that this is work in. Okay, so even though we take it as a negative minus, okay, eventually you see we get a negative out from it. So really this is a positive work going into the system. So which is why you get this. So it'll be much easier from the beginning that we just assume this to be work in. It's not a problem. Okay. So then from there, find out the boundary work because this is how much that we press. So then really how much the Q in. Okay. So in this case, when the Q in, you get negative. So it really means it's an out instead of in. Okay. So that's how we can solve the closed system for ideal gas system. Okay. So again, it's about finding the state in state 1 and state 2. Okay. And the work and heat is really happen in between here. So either we find out the state, the respective state, and we'll be able to find out the heat and the work itself, or the other way around. By knowing the heat and the work, we can find out the state that we want. Okay. So more or less, the question for thermodynamics always looks like this, more or less. It's either finding the property of a new state or you're finding the work involved in the process. Okay. In fact, if you don't think this as a just thermodynamic, any engineering question looks something like this. Later on in the solid mechanics, the second half of this this subject here, is basically the same, more or less the same. The concept is the same. You have the load here, and then you have the state of stress here. From this load, you want to find out the stress. Here, initially, it will be 0. For solid, it will be much easier. Okay. Or from the stress, you want to find out the load. It's the same thing. Okay. If you look at your core subject, electrical, most of the time the same as well. You have the work, you have the energy go in, which now you know is actually thermodynamically we call it the work, basically electrical work. Then you have a different state as well. State number 1, state number 2. Okay. So really every engineering problem are more or less the same. You, from the process, you find out the new state, or from the new state, you find out what happened in the process. Okay. Right then, there are a few more examples towards the end here, which I can let you try it out since the explanation are all here already. Is regarding isochronic, constant volume, constant pressure, and constant pressure and volume. Yes. Okay. So do try it out. Okay. But this is basically how the analysis for closed system more or less looks like. Okay, in the absence of a mass exchange, there's only heat exchange, there's only work exchange. Okay? Remember the core equation that we are writing. Okay, this all equal to delta E, and delta E in terms is basically delta U plus delta kinetic energy plus delta potential energy. Okay, so if there is no elevation, basically these are 0, which means this equal to this. Okay, and if it's a closed system, then obviously this is 0 as well. Okay, so then everything just from there. This is how the equation governing the system, basically. Okay, and the week after the semester break, we'll be looking at open system. By then, this will not be constant anymore. Okay, right. So that's how energy balance is. Okay, and I notice the time is already 5 o'clock. So I think we should probably stop the class already. So please try the example. Okay, and next class we'll look at probably 1 or 2 past year question, or maybe we'll go into the open cycle first, open system first. Then we'll look at the past year test 2 question together. Okay, what kind of question you can expect, and for you to practice. Okay, and then I'll make that as your assignment as well for you to practice. Okay, but for now, please go through the example in the lecture note. Okay, right then. So I'll stop here. Thanks very much again for joining the class today. So enjoy your semester break next week, and I'll see you guys in the week after next then. Okay, so thank you very much. Yeah, that's all for today.
All right, thank you, Doctor. And how about the attendance?
It's already taken. Since it's online, I have your attendance.
All right, Doctor.
Okay.
Noted.
Right,
Thank you.
thanks.
Thank you, Doctor.